Okay, sorry for that. We are starting registering only now. I just forgot. Apologize. All right. So do you see the whiteboard from home?
Yes.
Okay. Okay. So let's see how to write properly the quark current at the quark gluon vertex. Okay, so let me first of all draw the vertex. So quark here, quark there, and we have a gluon here. So this is our vertex that we can call nu. Now we have to specify the four momenta, so P1 and P3, simple. And in addition, we have to specify the color. Okay. So let's call color I here and color J there. And now let's write the current of this vertex, okay, by simply applying the final rules, the one that we know already. So the J to Quarks gluon, okay. So first of all, we have to take the adjoint spinor on the final state, then the vertex factor, and then the spinor in the initial state. Okay. So this is Q3, as you would say already from QED. But now we have to take into account also the color part of the wave function, which has to be Hermitian complex conjugate. Okay. So this is J, because we are in the final state, and Hermitian conjugate.
Sorry.
Yes.
Could you repeat the notation for the J mu? So it's Q, because it's difficult to read actually with.
Okay, so mu is just to label the vertex.
Mm-hmm.
I and J are the labels for the colors of the two quarks.
Okay.
And so when you take the wave function, you have to multiply your spinor with the color component, which for the final state is J.
Okay, and J mu, it's QQG. Sorry.
This is QQG, yes, quark gluon vertex.
Okay.
Okay?
Okay, thanks.
Okay, so the next piece is the vertex factor, okay, that we discussed before. So this is minus I, D strong, and then we have the Gaussian matrices here, lambda over alpha. And then we go to the initial state. The initial state we have U of P1, and then we have electric first layer, fourth component, Ci, and then U of P1. Okay, so initial state with function, vertex factor, sorry, state with function, vertex factor, initial state with function. Now, here we have two objects. Okay, so we have a 3 by 3 matrix, which is a Gaussian matrix, and this acts only on the color vectors. So these are only on this side here, and on this side there. And then we have the Dirac matrix, gamma mu, which instead acts on the spinors. So these are the spinor here and there. And so we can decouple the two. We can factorize these two components, the color part and the Dirac part. So we can write this as minus 1/2 ES I. So we put outside the constants. Then we factorize here all what concerns the color part. So we have Cj dagger, then we have the Gaussian matrix, and then we have Cj. And then we put the standard Dirac current, that is U bar 3, U1. Okay, we're just factorizing the two because they don't speak each other, essentially. Now, what is this object here? This object here we can write in a more compact way as lambda alpha j I. And as we will see in a moment, is essentially, this is a number. This corresponds to the j element of the gamma alpha gamma matrix. This is a 3 by 3 matrix with 3 rows and 3 columns. This is just the j element of this matrix. Okay, so this is just a number again. And so overall, we can write our current, okay, as minus 1/2 I yes lambda alpha j, and then we have the standard vector current U3 gamma mu U1. Okay. Okay. Now back to the slide. So let me summarize here what we found on the board. So this is indeed the current that we just derived for the quark-quark gluon vertex. Okay. It was our starting point. This is our arrival point, where now we have this matrix element put here explicitly. And this is the corresponding QED vertex, the one that we know already. So this is electron-electron photon scattering, or photon vertex, okay? Where, as you can see, apart from the appearance of this matrix element, the Gellner matrix element, the structure is exactly the same, okay? And this has, of course, important consequences, because apart from this coefficient that I put in red, okay, then the structure of the two currents are exactly the same. And since we know that parity and then also charge conjugation properties are conserved in QED thanks to the vector form of its current, then of course parity and charge conjugation are also conserved in QCD because they share the same vector current. Okay, we can show formally. Okay, it will be just a repetition of what we showed already for QED. As we will see next in the course, parity is not conserved in weak interactions because the shape of the current is different. It's not a vector current like this. Okay. Now, what about antiquarks? So let's now consider the antiquark gluon vertex. Okay. So the difference when you look at the diagram is now that by convention the arrow point backward in time. This is the standard Feynman convention for final rules. Okay. And since now the current flow in this way, when you calculate your current, you have to move the other way, the opposite way. This is the mnemonic rule that I told you a long time ago. Okay, so here in this case, the first term is now regarding the initial state. And since it is now an antiquark, we have to use the antiparticle spinor B. So it is, which come adjoint. So it is adjoint VP1, then we have its color vector conjugate, emission conjugate, which is the I, because it is in the initial state here. Then we have the standard vertex factor, and then we have the final state. Okay? And also similar, one can do exactly the same derivation that we made before on the blackboard. So also here, of course, you can factorize your color part. You can denote these in the compact notation, because it's just a matrix element, okay? And you're done. So the difference is that now, of course, your current deals with antiparticle spinors.
Sorry, I have a problem. I can't see. Are you on the presentation now?
Ah, you cannot see the presentation?
Maybe it's just me, but I don't seem to be able to see it.
Marianna, tu vedi le slide? Let me try again. Can you see the slide?
Sì, io le vedo.
Okay, then?
Now I can see it. Thank you.
Ah, okay. Okay, so let me just repeat very, very quickly what I was saying. So this is now the anti-quark gluon vertex, okay? So the only difference is that you have now to use the anti-quark Dirac spinor, so the V instead of the U, okay? And since now the current flow in this direction by convention, then you have to then the adjoint spinor must be the one in the initial state, so the opposite way around, okay? Otherwise, all the rest is the same. You can again factorize your color part here, and you can write down your current in this way, okay? Where this lambda alpha ij is now the element, the ij matrix element of the lambda alpha gamma matrix, okay? It's just the same. Now, what about the gluon propagator? Okay, so we're studying QCD that in QED that the propagator is minus I g mu nu divided by q square. So here we have an additional object, which is this delta Dirac here, AB. So in QCD, one denotes the gluon as AB, okay? And this delta function here, delta AB, ensures that the gluon type A emitted at the vertex mu is the same as that absorbed at the vertex mu. And why is this relevant now? Because this is not obvious in QCD, since gluons can interact among themselves, okay, through the triple or cortical vertex that I showed before. So, and if a gluon interchange appear through one of these self-interactions, then this might result in a non-conservation of the color charge at the vertices. So this is why we need to ensure that the same gluon is emitted at the vertex and absorbed at the other vertex. And this is done by the introduction of this delta function. Okay. Now, once more, the non-abelian nature of QCD implies that gluons must carry color charge. And more specifically, color conservation at the vertex requires that gluon must carry not just color, but a combination of a color and an anticolor. Let's see how this works. Okay, so let me take as an example this Feynman diagram here, which is a three-level QCD scattering between quarks through gluon exchange. So here you see the levels of the colors. For instance, this is a red into blue and blue into red example. And we can see the flow of colors in this side diagram here. So the red flows in this way, from top to bottom, from top left to bottom right, and the blue from bottom left to top right. And this we can actually split in the two time ordering. If you remember, Feynman diagrams actually include all the possible time orderings. Okay, so this we can split now to understand better what is going on. So in the first time ordering, it is a blue quark, okay, that radiates a blue anti-red gluon. Okay, in this way, the anti-red cancels the red here and cancels the red there, and so we have our blue flowing in this way, exactly the way it is depicted here. Similarly, then you have to add this to the other opposite time ordering, where it is now the red quark that first emits the gluon, and it emits a red anti-blue gluon. So this anti-blue component cancels the color here and there, and at the end you have a flow of the red color in this way. Exactly this is represented here. Then clearly the physics process, which is represented by the Feynman diagram on the left, includes both possibilities. Okay. Now, to be more precise, gluons form an SU3 octet of doubly colored states. And you see here all the possible combinations. Red anti-green, green anti-red, red anti-blue, blue anti-red, etc., etc. Okay? There are 8 and only 8 possible. And if you look at the structure of this octet, you realize that it is exactly the same as that of the quark anti-quark octet that we found in SU3 level. The algebra is exactly the same. So it's equivalent to UD bar, DU bar, US bar, SU bar, etc., which corresponds to the meson that we studied. Okay. Now, the important point is that there is a precise correspondence between the 8 gluons and the 8 generators, so the 8 gamma matrices. And the correspondence is given here. So the lambda 1 and lambda 2 corresponds to exchange of red anti-green or green anti-red gluons. Lambda 4, lambda 5 corresponds to exchange of red anti-blue, blue anti-red gluons. lambda 6, lambda 7, green, anti-blue, blue, anti-green, and lambda 3, lambda 8 to these more complicated combinations. Okay. So there is essentially a one-to-one combination between correlation between the SU3 generator and the color of your gluon that you're exchanging. This you can also visualize here. So in the first example, we have a red quark that radiates a red anti-green gluon and goes into green gluon. Or another example, a blue quark goes into a green quark by exchanging a blue anti-green gluon, etc. Let me just focus on these two examples here. So this example where the red anti-blue and blue anti-red gluons are exchanged, okay? And these, so what I want to say here is that the gluon corresponding to lambda 4, so this guy here, can only contribute to these two possible exchanges, so red to blue and blue to red. And let's show me this in the blackboard. So let's consider a transition between a red to a blue quark. Okay, so you can write it this way. Okay, so let's check the case where this transition is mediated by a lambda 4 generator or general matrix. Okay, so this we can write in several equivalent ways. So one way is this first R lambda 4 B. Or in terms of the C vector that we are including, so the red corresponds to C1, if you remember, C1 daga, then we have number 4, and the blue corresponds to the C3, the notation that I introduced before. Okay, so these are three equivalent ways of saying the same thing. Let's now make things explicit. Okay, so the emission conjugate for a real vector is just the transpose of the vector itself. So this is just 1, 0, 0. Then we have the gamma 4 matrix, which is 0, 0, 1, 0, 0, 0, 1, 0, 0. Then we have the blue color vector, which is 0, 0, 1.
Apologies, it's got all blurred for me, I must say. I don't know if it's the same for Mariana as well.
Sorry, I cannot hear you.
Sorry, it's gone. Ah, it's back. Sorry, it had gone completely blurred for a minute or two.
I cannot understand you. Let me check if I can raise the volume somehow.
No, it's okay. It's back. It's just that the image had gone completely blurred for a minute or two.
Ah, okay. Maybe it's your connection, maybe.
Yeah, maybe I've got problems there. Yes.
Mm-hmm. Ah, can you speak again, please?
Is it better now?
Ah, much better. Okay, I just raised the volume. I found how to raise the volume. Okay, thank you. So let's now take the product of the matrix with the vector, which is 3, 0, 1, 0, 0, 0. So this is just 1, 0, 0, and then we have 1, 0, 0. And so at the end, this is just a number 1, which is clearly not 0. Now, as I was telling you before, this guy here is nothing else than the 1, 3 matrix element of gamma 4. So this is the gamma or 1, 3. Okay. And so this is indeed this guy here. 1, 3. And in fact, it's not by chance that we got 1. It is indeed this matrix element. Okay. Let me take now the opposite transition. So now we move from blue to red. So this is blue daga, 4, red, or equivalently C3, C3 dagger. Gamma 4 and C1. And so we have 0, 0, 1. Then we have on the 1, on the 4, so 0, 0, 1, 0, 0, 0, and 1, 0, 0, and now we have 1, 0, 0. Again, we take the matrix vector product. So this is 0, 0, 1, and this gives you 0, 0, 1. And so again, you get 1. And in fact, this is the lambda 4 3, 1 element, which is this guy here, which is exactly 1. Okay. Now let's take a different color transition, but still mediated by the lambda 4. What happened? Okay. So let's now consider, for instance, green to red. So this is C2 dagger, lambda 4, C1, because it is 0, 1, 0. Then we have 0, 0, 1, 0, 0, 0, 1, 0, 0, and then we have red, so 1, 0, 0. Again, you take the product. So this is 0, 1, 0. And now we get here 0, 0, 1. Now, when you take the product of the two vectors, you get 0. This, again, to tell you that the lambda 4 gamma cannot commute a green into red, but only blue into red or red into blue. You see, of course, this works for all the other combinations. Okay? So to be more explicit, what happened here? So we found that C2 dagger, lambda 4, C1 is 0. And so if we write now the current, the way we did before, for this specific combination, J equals 4 Gluon, and then we get minus 1/2 pi ds. Then we have this C2 dagger lambda 4 C1, and then we have the standard current U 3 gamma mu U1. Okay. But this guy is 0. And so there is no current associated to this quark exchange combination. Color exchange combination, sorry. Okay. Let's go back to the slide. Now, in the calculation of the matrix element of any QCD process, one of course needs to account for the different combination of quarks and gluons that can contribute. Okay, so we will take now an example, which is the UV QCD scattering at 3 levels, so mediated by a gluon. Okay, so this is the full Feynman diagram. So we have the 4 momenta, P1, P3, P2, P4, and the color indexes, I, K in the initial state, and J, L in the final state. Okay. Then we have the gluon exchange. So the exchange gluon is labeled by A and B, okay, and the delta function ensures that it is the same gluon. Then the incoming quarks colors are IJ, the outgoing are JL, and so the color flow in the diagram is IK in the initial state to JL in the final state. Now, in the strong scattering process, the color of each quark involved is equally likely to be red, blue, or green. So the probability that this quark is blue or red or green is the same, we don't know, can be any of those, and the same for all the others. And in principle, also all possible gluon color and color combination can take part here. Okay, so one can compute that indeed there are up to 648 distinct combinations of quark colors and gluons that can potentially contribute to this process. But we are lucky, as we will see after the break, because at the end one can average all these objects, and at the end you end up with a single number. Okay, so before doing that, let me make one step more on the whiteboard. So let's calculate the matrix element of this process here. Much like the way we did it for the model scattering. Okay. So let me draw a line. U quark, U quark. Let's start with the D quark. Then we have our vertex mu, our vertex nu. The gluon is the GAP, so this is A, and this is G. Now we have the core momenta, P1, P3, P2, P4, and we also to indicate the colors. Okay, so it's P1 I, P2 K, P3 J, and P4 L. Okay, now we have all the ingredients, and we can just apply the Feynman rules, the one that we studied already for QED. So the object we want to calculate is minus y m fi. And so we have the current at the upper vertex, the propagator of the gluon, and the current at the lower vertex. So the first part is the current at the upper vertex, where we already know. So it's U bar P3, C delta J. Then we have the vertex factor minus I GS and mu 1/2 lambda A. And then we have the state, the initial state. So it is a U, now first the color part, CI, right? And then U C1. So this is the vertex, the current at the upper vertex. Now we have the gluon propagator, which is minus I G mu divided by 2 squared times the delta function. And then we have the current of the lower vertex. So this is going to be U bar 4 C L daga. Then we have the vertex factor minus I GS gamma mu 1/2 lambda B. And then we have the initial state, so this will C K U P2. Okay. Now the next step, as we already did before, is to factorize the color part with respect to the Dirac part. And let's do this separately for the upper and the lower vertex. So on the upper vertex, we have C delta J lambda A, Ci. Then we have all the rest. That is U bar 3 minus 1/2 I GS mu U1. Then we have our and the same and I G mu over Q squared E. And then we have do the same thing on the lower vertex. So we factorize again the first part. So here we have CL daga lambda B CK. And then we have the U bar 4 minus 1/2 pi US gamma mu and U equal. Okay. Now, this is lambda Ji, okay, the Ji element of the lambda A matrix, and this is lambda B Lk element. Okay, so we can now put everything together. So we have minus GS squared divided by 4. Then here we collect all the color part. So we have the lambda A G I times the delta that we put here, and then the lambda B the Lk. Okay, and now we have all the rest. So is the U bar 3 mu U 1. Then we have minus I G mu over Q squared, and then we have the last second term, which is mu bar 4 gamma mu U P2. So this term here is the analog, right? It's just the same as the Moller scattering. What is new is, of course, the color part here. So let's now multiply Vivo's minus I MFI. Let's divide by minus I. So we get the matrix element itself, MFI. So this is minus GS squared by 4. Over here. Now let's now act the delta function here. So once you do so, it is nothing else than delta A at K. You agree? So here we have delta A Ji delta A Lk, right? Then we have G mu divided by Q squared, and then we have just the two vector currents. This likely we can write as minus GS squared times something that I will define in a moment, IK into LJL, and then we have all the rest. Where this new object that I just introduced for the C ik into JL is given by 1/4, that we take from here. And then there is, of course, an implicit sum over A. And then we have lambda A Ji lambda A Lk. And this guy here we call color factor. Essentially, this object encodes all the possible color combinations that can take part of the process. Okay. One more word on the slide, and then we make a break. So this is what we obtain. Okay, this is the matrix element for the 3-level quark scattering in QCD. Let's compare this with QAD, so to the molar scattering. Okay, the one that we derived at the molar scattering is reported here, where GE in the case of QAD is just minus the electron charge, or the electron charge, which is negative. So now let's compare the two. Okay, so the QCD matrix element for a particular combination of 4 colors can then be obtained from the molar scattering matrix element with two simple substitutions. First of all, of course, the Kaplan constant, GE becomes GS, okay, and then by multiplying this by the color factor. So the color factor encodes all the information about the color interaction inside to the process. So more explicitly, it accounts for the sum over the 8 possible exchange gluons and all initial and final state color combinations. Okay. Ok, let's stop here for riprendiamo 25, ok? So we recombine at 12:25. If you have questions, of course, you are free to work on. Okay.
Io ho studiato la teoria online, non ho lasciato la parte e anche tutti gli esercizi che ho fatto mi chiede cioè si fa l'AI function e faccio cioè magari si può più fare ti spiegavo questo slide per la classe, non lo spieghi, ve lo dico fare esempio. Io qui non ho studiati, cioè io mi stavo prendendo e ho dopo e vabbè. Prima c'è questo, io era una sessione a me, sempre comprato e tutto qui, poi Mi sto chiedendo se sto facendo con lui intelligenza artificiale. E come? Un po' pesante, cioè molto chiudo come corso secondo me, però lui sì. A me piace io perché mi devo creare quel primo semestre, cioè a me mi piace perché capisci quando spiega. Allora, a me l'intelligenza artificiale, cioè a me ce l'abbiamo, c'era 2 volte, 2 ore e mezza di pomeriggio, 1 volta per 2 ore e anche altre per 2 ore e mezza. Per fare cose belle, io mi muoio. Perché a me non fa mai anche le prime lezioni di metodi, una dopo le chiamate mezza piene, cioè di alla fine che non sono le figure. È tutto molto teorico, cioè non fa niente, no, la storia del niente, ma non fa niente su Inter. Anche il primo anno, no? Che lo insegna. O no? No. No. Ho capito da quando doveva dedicare il primo anno. Allora, un corso di strategia. Sì. Non ti senti un po' in successione, anche che fa anche quelli del che fanno il dottorato. Ah, perché noi poi scritto come vero. Ok. No, però mi è stato un po' sul cazzo. Sì, perché è molto personale. È molto personale come ti fanno queste storie da utilizzare. Mi ha dato 29, perché a me era la prima. Ora è stata più sulla situazione del 9, cioè se stava zitto era meglio. Perché mi ha detto che quando vado di ragionamento del fatto ci sono sempre arrivati alla risposta giusta, ma non precise. Per quello, cioè secondo me nel senso, non è che sono arrivata dal come lavoro di ragionamento, quindi sono arrivata a tutto, cioè non di niente. Perché io tipo un pezzo che mi fa l'entra, cioè ho parlato perché quando le risposte sono interessate, faccio un po' di perfetto, ma effettivamente mi è interessante. Perché no, io penso che gli assassini quando non ti do una lode, perché magari mi hai un certo così che non vedi che se sei abbastanza bene, del genere comunque di una si ricorda anche la quando mi che lei mi fa guarda il voto per festa è 29 quindi ho fatto 5 serie di pausa e ho fatto a 29 non si va io 30 cioè 29 cioè che guarda 29 no vabbè non sarebbe la carità però neanche la 28 e fa dopo il magari che ho provato un sacco di idea no poi era convinto che era una forse non c'è che non lo subito perché quindi esce guarda una posizione esperienza io sono un consiglio quello benissimo passare da che fanno anche lì la mia coinquilina quest'anno ha preso la casa e voleva medicina e in vista dei prossimi 6 anni infatti si è presa la casa. No, che io l'ho tenuta perché tanto so che noi bene o male ogni tanto veniamo, quello ogni altro anno, ok, però se uno non ha il alfa.
Theta? Okay, so we can restart. Do you still see the slides at home?
Yes.
Okay, so we introduce these color factors that account for the possible combination of possible combination of color exchange between the quarks participating to the process. So let's now understand better what it is and how to calculate it. So, so each of the individual color factors can be associated with the exchange of a particular type of gluon, as we will see, okay, and in such a way that the color charge is conserved at vertices. So we can consider 4 different categories of processes, and for each of them we will calculate the color factors. So the first category is this one here. So we have is the most simple one. Okay, is red into red. Okay, so the color index is 1 everywhere. All colors are the same. The second category is that 2 initial state quarks have different colors, but they do not interchange color. So it is red-blue into red-blue. The third category is in the case where they are different and they also exchange color. So red-green into green-red now. And the fourth category is when all 3 colors are involved. So red-blue into blue-green. Okay, so let's start from the first category, which is reported here. So this is a red-red into red-red process. So we can calculate now the color transitions at the 2 vertices, which are, of course, the same in this case. This is C1, C1, and C1, C1. So in both cases, for the upper and the lower vertex, we get the lambda 1, 1. Okay. Now, the zero contribution to this process arises only from the lambda 3 and the lambda 8 Gell-Mann matrices. Why? Because they are the only matrices that have a non-zero value in the 1, 1 element. You can check all the Gell-Mann matrices, and you see we are interested in the lambda 1, 1, right? And only those 2 are the ones that have a non-zero element, a 1, 1 element. So these are essentially only the 2 types of gluons that can contribute to this process. So let's see how. Now I have to switch here. Okay, I'm going to the blackboard. So let me first write down the lambda 3 and lambda 8. So this is 1, 0, 0, 0, minus 1, 0, and 0, 0, 0. And the lambda 8 is 1 over square root of 3, 1, 0, 0, 0, 1, 0, 0, 0, minus. Okay. So let's calculate our color factor. C red into red, which is equivalent to C 1, 1 into 1, 1. And so we apply the definition. So the definition, if you remember, is 1/4. Then the sum of R equals 1 to 8, and then we have lambda up 1, 1 times lambda 1, 1 in this case. Of course, one should have here all the possible combinations, but we know that the other are 0. Okay. So out of this sum here, only 2 contributions survive, which are the one corresponding to the lambda 3 and lambda 8 matrix, because all the other have this element vanishing. So this is just 1/4, and now we have lambda 3, 1, 1 times lambda 3, 1, 1 plus lambda 8, 1, 1 times lambda 8, 1, 1. So let's now just substitute the values. So this is 1 over 4. Lambda 3, 1, 1 is just 1. So this is 1 times 1 plus lambda 8, 1, 1 is 1 divided by the square root of 3. So this is 4, and then we have 1 plus 1/3. So this is the end. 1/3. Okay. So we did it for the specific case of red into red, but of course, due to the properties of the Kelman matrix, this is the same also for green into green and blue into blue. So back to the slide. Okay, so sorry. So considering the first category and all the three possible color cases, we get one term, in all of these cases. Okay. Let's now consider the second category. Okay. So in this case, we have red-blue into red-blue. So they are different, but they do not exchange color. So in the upper vertex, the transition is 1 into 1, and in the lower vertex is 3 into 3. Okay. So the elements that concern us are lambda 1, 1 and lambda 3, 3. And the only Gell-Mann matrix, so the only QCD generator that have this element non-vanishing is lambda 8 again. All the other, they have to be both simultaneously non-zero. Okay, so this is only possible for the lambda 8. All the other cases, they're vanishing. So let's go back to the blackboard. So in this case, we have red-blue into red-blue. So this is 1, 3, 1, 3. And so here we have lambda 1, 1 lambda 3, 3. Okay. Now we sum up to the 8 Gell-Mann matrix, but only one is provided non-zero contribution, which is the lambda 8. So this is simply 1, 4 lambda 8 1, 1 times lambda 8 3, 3. Okay, lambda 8 is here, so we have 1, 4. Lambda 1, 1 is 1 divided by square root of 3 times minus 2 divided by square root of 3. This is going to be 1/4 divided by minus 1/3, which is minus 6. Okay, let me jump again in the slide. Okay, as before, the same value occur for all the possible cases of this category. Okay, so all the combinations that don't change color, like these, all have a color factor equal to minus 1/6. Third category, now we have red-green into green-red, so we exchange the color, but we still have only two colors involved. So in the upper vertex, we have 2, 1 in the upper vertex and 1, 2 in the lower vertex. Okay. Same game, we search for Gell-Mann matrices which have simultaneously 2, 1 and 1, 2 element non-zero, and this only occurs to the lambda 1 and lambda 2. Okay. So again, we can go back. So the lambda 1 is 0, 1, 0, 1, 0, 0, 0, 0, 0. The lambda 2 is 0, minus 5, 0, 5, 0, 0, and 0, 0. So we are now interested in the color factor red-green into green-red. So this is 4, and 8, 1 to 8, and then we have 2, 1 times 1, 2. And we have two contributions from the lambda 1 and lambda 2. So here is 1, 4, and then we have lambda 1, 2, 1 times lambda 1, 1, 2, plus lambda 2, 2, 1 times lambda 2, 1, 2. Let's pick up the values from the matrix. So lambda 1, 2, 1 is just 1. So this is 1, 4. We have 1 times 1 plus 2, 1 is minus 5 times 5. All right. So this is 1/4, and then we have 1 plus 1. So this is 1. All right. And again, one has to consider all the possible combinations that belong to this category. Okay, for all of those, it is +1/2. Now the last category, red-blue into blue-green. Okay, so using the same approach, we get lambda 3, 1 at the upper vertex and lambda 2, 3 in the lower vertex. However, when we now search into the Gaussian matrices, we will not find any of them having simultaneously 3, 1 and 2, 3 element among 0. Okay, so in this case, sorry, trivially the color factor is 0. And this is not a surprise because this kind of color transition would not ensure color conservation at the vertices. So it must be 0. What about now anti-quark? Okay, the situation is pretty much the same. Of course, when calculating now the current, one has to take the other way around, okay? Because the arrow pointing in this direction, right to left, so we have to move left to right. So in this case, the first color is I, and the second is J in the upper, and in the lower, again, the first is K, and the second is L. So this is a pure Q-bar scattering. Then we can have a mixed case. So we have a Q-bar scattering. So, of course, the currents flow in the opposite direction. So in this case, the order is Ji in the upper vertex and KL in the lower vertex. And finally, you can also have S-channel processes like this one. Okay. Again, we use the same rule. So the current flows like this. So we start from the opposite way around. So for the anti-quark, we have KL. So we have KL here at this vertex, and instead we have KI and JL. Okay. Now, it turns out that from the properties of the Gaussian matrices, it doesn't matter if it is a quark or anti-quark. At the end, you get exactly the same value for the color factors. And you see here the case. So the CRR, red-red into red-red, is the same as red anti-red into red anti-red, or the same as anti-red anti-red into anti-red anti-red. For all cases, you get 1/3. And the same for others. Okay. These are for the two S channel, the three T channel that we consider, and also for the S channel we have these values here. Okay. So at the end, one end up with the numbers, simple numbers. Now in the strong scattering, the color of each quark involved, as we said before, is equally likely to be red, blue, and green. Okay. So in principle, if you don't, you cannot know, and since you don't know, you have to take the average of all the initial state and sum over all passive translate colors. Okay. So we do the same way we did already in the QED, for instance, down from the color chart. So we calculate the color average squared matrix element, where essentially you average over the initial state color and you sum over the final state colors in order to take all possibilities into account. Okay. So let's now calculate this average value. So this is general for the matrix element. Okay. And we are only concerned with the color part. So for the color part, what we need to calculate is this quantity here. Okay. Where these are indeed the color factors. Okay, now we have already calculated the color factors for all the relevant cases. We have 3 times the value 1/3, 6 times the value is minus 1/6, and 6 times the value is 1/2 when you sum. So when you put everything together into the sum, at the end you get with 2/9. Okay, so at the end things that were completely extremely complex at the end up with a simple number, 2/9. So the entire effect of these 648 possible combination of quark colors and gluon exchange at the end result in an average color factor of 2/9. Okay, and this is the same also for quark antiquark or for antiquark antiquark and for each channel. Doesn't matter. 2/9. So easy. And now we can again compare the cross sections, for instance, for a QED and a QCD process. Okay, let's take the differential cross section for the scattering for the molar scattering that can be written in this way. Probably you've seen already this in QED, yes. And then we have the analog now for quark scattering in QCD scattering instead. Okay. So there is a small difference here because here you see S, which is the Mandelstam variable for the 2 electrons, or the 2 leptons, whatever, or fermions in general. In this case, you have S hat. You see, the reason is that this corresponds to the square center of mass energy of the quark-quark interaction. But you can never make a beam of quarks or a target of quarks. You can only use hadrons, right? And so you have to scale the center of mass of your hadron collision into the one you need here for the quark-quark collision. Okay, so the value X is different. This will be more clear even later in the course. So the QCD cross-section for the scattering process, quark-quark into quark-quark, can be obtained simply starting from the molar scattering, QED molar scattering, by replacing, as usual, the coupling constant, so alpha electromagnetic with alpha strong, and by multiplying by 2/9. And this takes account of all, in average, all possible combinations of color exchanges. Very easy. Okay, let's now change topic. So when quarks were proposed back in 1964 by Bellman and Zweig in the quark model that we studied last week, essentially, in order to interpret the multiplets, essentially. Of course, that model was rather elegant. It was able to explain the multiplets, all these regularities between hadrons, but it is a model. And in order to make this a reality, you have to try to experimentally detect the quarks. Otherwise, it's just a model. It's just mathematics, right? So the model predicts the existence of 3 quarks, up, down, strange, but then you have to find them experimentally, right? That's how physics works and all science works. So searches for 3 quarks were conducted at accelerators with every kind of beam particle, hadron beam, muon beam, neutrino beam, photon beam, whatever, and also by searching in cosmic rays. They were also searched in millican type experiment. You know the millican experiment with the drop of oil. This was quite straightforward in this case because the quarks are predicted to have a fractional electron charge. So it will be quite easy to find them with a millican type experiment. No way. People were so disparate that they also started to search quarks as a deposit in substance ranging from the oyster shell, il guscio delle ostriche, la disperazione, in moon rocks, in whatever thing. No way. No way. All these searches failed, leading to the wrong conclusion that quarks must be extremely massive and very tightly bound into hadrons, so that it would be very hard to pick them out of hadrons. Now, today we know, of course, the answer, and we will study this next week. The experimental evidence of quarks is now, of course, well established through deep inelastic scattering experiments that we will study next week, indeed. And the experimental evidence are actually consistent with quarks being light quarks, of course, up, down, strange, light quarks, and quasi-free inside the hadron. So in complete antithesis with the original hypothesis of a massive and strongly interacting object. Okay, this will be clear next week. Now, how can we understand why free quarks are not observed in nature? And there's no way to observe them. So the non-observation of free quarks is explained by the hypothesis of confinement. And this hypothesis tells us that colored objects, so objects that carry color charge, non-zero color charge, are always confined into color singlets, so into hadrons. Okay? No object with non-zero color charge can propagate as a free particle. Or in other words, no isolated color charges can exist. And there is no way one can separate a quark from a hadron and observe it as a free object. No way. This is QCD. Now, color confinement is believed, let me stress, believed, to originate from the gluon-gluon self-interaction, okay? Which makes the huge difference between QCD and QED, of course. Which in turn is a consequence of the fact that the gluons themselves carry color charges, as we know now, okay? So why believe? The point is that today, at present, there is no formal proof of this. There is no way to use QCD from first principle to prove confinement. And why? Because confinement is a feature of the strong interaction that occur at low energy, or if you like, at large scales. And as we will see tomorrow in the next lesson, this corresponds to values of the coupling constant alpha strong, which are extremely large, order of 1. And if your coupling constant is order of 1, you cannot use perturbative techniques. You cannot make calculations, essentially. So confinement is in a region of QCD, which is called the non-perturbative region of QCD, where you cannot use the theory itself, and of course you cannot use the perturbation techniques to make predictions. And that's why QCD is so hard to study. The only way is to make experiments in this region. So in this regime of non-perturbative QCD, analytical calculations are extremely complex, actually impossible. And the theory is not predictive. Okay? Of course, as we will see tomorrow, there is another range of QCD, which is the perturbative QCD, which is the region of very small distances, very high transfer momenta. In that case, the alpha strong constant becomes small enough that you can apply perturbative techniques. And so you can make calculations, and the theory becomes predictive in that range, not in this range here. So let's consider what happened when two quarks, for instance, a quark-antiquark pair, are pulled apart. So suppose you want to separate them, okay? Now, the interaction between quarks, of course, occurs through the exchange of virtual gluons, okay? So the two quarks are linked by gluons, but gluons interact each other. They self-interact. So, since they carry charge. So, there are attractive interaction between these two gluons, which are mediated by other gluons, as you see here in the picture, okay? And the result of this is that, so the effect of this is that these attractive interactions squeeze the color field into a so-called color flux tube, as you see in the image here. Now, at relatively large distances between the quark and antiquark, the energy density in the color flux is constant. So we are now in this region, in this intermediate region here. You see where the color flux is, they are all parallel, okay? So in this region, the energy density stored in this gluon field is constant. And this means that the more they are far away, the longer, the larger is the volume of this region, the higher is the energy inside this region. So let me read again. At relatively large distances, the energy density in the color flux tube is constant. Therefore, the energy stored in the tube is proportional to the separation of the quark. The larger the separation, the more the energy you have inside. Okay, because it is constant. And so at the end, this results in a term in the quark-quark potential of the form Kr, so proportional to the distance. The more you pull them apart, the higher is the energy you need to separate them. And this goes to infinity. You see, R can diverge. So the constant K that you see here is called Sling Tension, and it is found experimentally to be consistent with a value of the order 1 GeV over Fermi. And this value corresponds to a huge force of the order 10 to the 5 Newton, okay, between the two unconfined quarks. That's why you will never be able to separate a quark and to observe it alone. Now, since the energy stored in the color field increases linearly with the quark distance, okay, one would need an infinite amount of energy to separate the quark-antiquark pair. That's the essence of confinement, okay? So the confinement hypothesis implies that color objects cannot propagate as free particles. Instead, they spontaneously tend to arrange themselves into bound states that are colorless, or white, if you like, combinations, so hadrons, or if you like, color singlets. So only color singlets can propagate as free particles. A proton can propagate because it is a color singlet. It is white. A quark cannot, or a gluon cannot, because they carry quark. What about mesons? Okay, so in particular, the mesons are color singlets with a totally symmetric color wave function that you see here. So it is completely symmetric. Red anti-red plus green anti-green plus blue anti-blue. Whatever you exchange things, you get exactly the same. Okay. What about, so this is for a system of quark-antiquark, which are mesons. What about the system of quark-quark, two-quark system? So as we've seen in the previous chapter about SU3 flavor, but the algebra is the same. When you combine two, when you combine two quark triplets, you end up with a sextet plus a triplet, if you remember. Again, the same for colors, because the algebra is the same. So you obtain here a sextet and a color triplet, but you don't get any color singlet. This means that no way you can get a bound state of two quarks. A bound state of a state of two quarks carry color, so it cannot be a hadron, not be observed in nature. What about three quarks now, which are baryons? When you now put together three color triplets, as you know already from SU3 flavor, you obtain a decuplet, two octet, and a singlet. And this makes a difference, because now we have a color singlet. Okay, so the three quark system can exist in nature because indeed they can combine to also make a singlet state. So all our baryons that we observe in nature are color singlet, okay, due to this color combination. And you see here now the color singlet wave function for baryons, which are indeed the permutation of all three colors, red, blue, and green. Now, this color singlet wave function is colorless, of course, it is white, otherwise it could not be observed in nature, and also totally anti-symmetric. Okay, if you exchange the order of 2, you get a minus sign on top of this. And since it is the only one possible for baryons, because it is the only way to get a singlet for three quarks, it follows that the color component of the baryon wave function is always anti-symmetric, as we anticipated, if you remember, last week. So last week we used this result to calculate now the spin flavor component of the wave function. If you remember, assuming that the baryon wave function, the color component of the baryon wave function is anti-symmetric. Now you understand why. Okay. Few comments. Of course, not only quark, but also gluons carry charge, and so they must be confined into hadrons. So confined apply to quarks, but also to gluons. Okay. So unlike photons, gluons cannot propagate over macroscopic distance despite being massless. We know that the range of the electromagnetic interaction is infinite because the photons are massless. Gluons are also massless, but the range of the strong interaction is 10 to the minus 15 meters, because gluons can only be confined into hadrons, and this is the dimension of hadrons. Okay, so order 1 Fermi. An interesting note is this one. So if nature had chosen a U3 local gauge symmetry rather than an SU3, then there would be a 9 type of gluon, which would come in this color singlet state, G9. Okay. Now, in that hypothesis, being now a core singlet, this gluon could propagate everywhere. It's a core singlet, so there's no confine anymore, okay? And so this would behave as a strongly interacting photon, resulting in an infinite range for the strong force. And of course, the universe would be completely different in that case. We have still 5 minutes. Okay. So as already anticipated by Gell-Mann back in 1964, in the framework of the quark model, in principle, there could exist several different combinations, hadronic combinations of quarks, okay, which must be, of course, also core singlet. At the time of the quark model, nobody knew about core, of course, but already Gell-Mann had the intuition that maybe one can have different combinations apart from baryons and mesons. And in fact, we do have many different possible combinations, which are all core singlet, so all detectable, all that can be propagated in nature as free objects. So one combination is the pentaquark, which is a diquark, antiquark combination. So there are 5 quarks inside here. Another is the dibaryon. Essentially, we have 6 quarks here: diquark. And the other possibility is the tetraquark. So we have a diquark, a di-antiquark combination. Or we can have molecules, okay, with a two quark antiquark pair, which are separated by some distance. Or we can have hybrid states that include both quarks and gluons. Or we can have pure gluon states as a gluon singlets, which we call glubal. Okay, so this you can predict already by QCD. Okay, the only requirement is that they have to be core singlet. Whatever complicated combination they have to be core singlet. Okay. Now, did we find this object? Yes, many of them already. So the first of these, so-called exotic hadrons, was discovered by the Bell experiment in Japan back in 2003. Okay, so 18 years ago. And today, more than 30, probably even 40 exotic hadron states have been experimentally observed. Although the quark-gluon structure and also the quantum number are not completely understood for all of them. Okay. So let me show you as an example. This is the charmonium family that we introduced last time. So below this dotted line, we have the so-called closed charm, so CC bar states. Okay. And above these, we have open charm state. We have a CC bar state that can decay into open charm because their mass is more than twice the mass of the d mesons. Okay, so let's say the lighter and the heavier charmonium state. Can you see in the yellow are those that are established, and in I don't know gray, whatever it is, blue, these are predicted but not yet discovered. But when we now include here all these these exotic hadrons, you see how this family enriches a lot. Okay, here we have the mass on the vertical scale and the quantum number in the horizontal scale. Okay, and in red are the neutral, and in blue we have the charged. So all these objects, which are denoted as X, Y, and Z, are not standard mesons nor standard baryons, of course, but are exotic objects. Some of them are understood in terms of the tetra quark or pentaquark or whatever. Some other are not yet. And there is an intense research activity in this. Okay. So let me just very quickly go through this list of exotic hadrons. So the first one is the X3872, the first of them discovered by the Bell experiment in 2003. Okay, this is the mass in MeV, this is the decay width, this is the quantum numbers, which are well established because now many experiments have observed this state. And these are many different possible decay modes. And then we have others. Okay, I will not go through all of them. Okay, and there's also a second page here for the Z, X and the Y, etc., etc. So there is you see somewhere we have question marks because we don't know yet exactly the quantum numbers for these objects. Okay, so of course new experimental data are needed. And then you compare your experimental data with the models, which are QCD inspired model, but not pure QCD because we are now in the non-perturbative region, so you cannot use perturbative calculations. Few examples. So the one I want to show you is the pentaquark, which is really very relevant. So after more than a decade of controversial results about the discovery of pentaquarks by many experiments, really many, this was finally observed and confirmed by the LXCB experiment at CERN in 2015. And indeed, two significant resonances were discovered in the decay of a lambda B0 meson into J K- proton decay. So the decay you see here, it is regulated by the weak interaction. So you see here the exchange of a weak boson W. So the initial state is a lambda B baryon, so it's a BUD baryon. In the final state, for a very small fraction of events, people observed this object here. So pentaquark with the structure of UC bar CUD, so UUD CC bar, which indeed UUD is nothing else, is a proton. No? CC bar is J. In fact, this object was observed to decay into a proton J plus a kern. Just to show you the results, this has been published in 2015 by LXCB. So here we have the invariant mass of the J proton final state, so the final state of this intriguing object here. And there is a clear peak here, okay, at a certain value of the mass. And when you make a very sophisticated analysis, you understand that there is not just one peak, but two peaks. We have a broader peak here at a smaller mass and a tighter peak here at a slightly larger mass. So only if you include both, you can fit your results here. And these are now the features of these two pentaquark states observed by LXCB. So the first is the PC 4380, which is this guy here. We have already a hint of the quantum numbers. This is the mass. The width is 200 MeV, it's quite large, okay? And the significance of this is 9 sigma, so well above the discovery level, which is 5 sigma. And the other one is this narrow peak, which is even more significant, 12 sigma, at the time where these data were published. Now, of course, we have collected many more data. But this is not the end of the story, because just a few years ago, in 2018, a new measurement was done at LXCB still to investigate this pentaquark structure, and it was discovered that actually this pentaquark structure is even richer. So essentially, two things were discovered more recently. First of all, a new pentaquark state at a lower mass, this guy here, okay, with a significance above 5 sigma, so above the discovery claim. And the one that was discovered in 2015 is actually the combination of two, okay? There are two resonances very close that are interfering here. And you can see these into the Darius plot. Okay, we included the Darius plot for three body decays, if you remember, a couple of lessons ago. This is an example where you plot the squared mass of two finite particles, the squared mass of the other combination of finite particles, and then you find that there are accumulation of events in some regions. Okay, so this one here corresponds to the sum of these two objects, these two resonances, and then this one here observed here is the new state also observed. Okay. What is now the interpretation? We don't know yet exactly, but the main current hypothesis is that this pentaquark is a sort of a molecule between a D0 or D0 star meson and a sigma C plus baryon. Okay. Another thing is the Theta Quarks. Also, this was observed by LXCB a few years ago. 4 different states, you see 1, 2, 3, 4, that you need in order to fit your experimental data in this invariant mass spectrum. And this is consistent with the Theta Quark with the structure CC bar SS bar. Okay. And you see here now more detail, the quantum numbers, the mass, the width, and also the significance, all above the threshold of 5 sigma. Okay. And let me conclude with this very recent plot. So this is essentially a summary of the hadrons discovered, new hadrons discovered at the Large Hadron Collider in the last 10 years. Okay, so you have in the x-axis the years, so the last 10 years, and here you have the masses, and here we have the quark structure of these objects. So some of them are standard baryons, some of them are standard mesons, but maybe heavy with a beauty quark or C quark, etc. Some other are Theta Quarks, interpreted to be Theta Quarks, like CC bar, PP bar, CC bar, etc., or Pentaquarks. You see here how they're distributed and Some of them have been discovered already this year. Okay. Okay. Enough for today. Any questions?
Yes, just a quick question going back to the pentaquark. Between sort of molecule approach and real pentaquark, what is the difference in QCD? So how do you make the difference in the end at the level of the equations?
I think the difference is in the quantum numbers at the end. And the quantum numbers are not fully accepted in the sense that RxCB has measured the quantum numbers for these objects, but with a certain uncertainty. And so we have now to cross-check these with the model predictions. And there are several possibilities, and the most probable seems to be this one that we put here. So it's a matter of quantum numbers.
Okay.
Okay. Vabbè, so see you then, not see you. La lezione domani, ok? Però online, chiaramente. So we have tomorrow, we continue at 9 a.m. from remote, 100% remote.
Arrivederci.
Arrivederci.